In the previous video, we introduced the Strum Liouville problems. I'd like to have a review of it. Maybe because talking about things in different ways can help us understanding them. So we have looked at a second order ODE that has this odd form in which we're giving quite some restrictions on how it appears, but it has also some extra flexibility than usual because lambda is a parameter in there, in the ODE that we're looking at, that we don't know when we have to solve for. We have some restrictions on px, it needs to be positive. Wx needs to be positive. We have some boundary conditions in which alpha and beta are not both 0 at the same time, and gamma and delta are not both 0 at the same time. And we're solving on it on an interval a to b, where a and b are real and not infinity. We want to solve for eigenpairs, that is, a combo of lambda being a real parameter and y being a function that satisfies our ODE. Together, they have to satisfy our ODE in a non-trivial way. We have stated that they're countable, so I can count them, giving to each of them an index n for n in the natural numbers, and they're distinct. Based on the Strum Liouville problem, we defined the operator h. H is a self-adjoint operator, and it's defined as minus px times y prime, all of it prime, minus qxy. It goes from the space of functions, from a space of functions to another space of functions, and both spaces have the boundary condition ingrained in it. We have introduced the inner product. This is an inner product that works on functions and not on vectors anymore. So we're looking at the inner product of two functions. The inner product is always something that you give twice the same thing, the same type of thing, and you retrieve a real number. So we give two functions, f and g, the sort of functions that h it can be applied to, so they need to satisfy the boundary conditions. And we define the inner product as being just the integral on the interval we're looking at, so between a and b, of f times g times w dx. W is sometimes called the weight for this reason. An inner product trivially defines a norm all the time. So you can define the norm as of some function f as the inner product of f times f at the power 1 over 2, so the square root of the inner product of f by itself. In this, both for the inner product and for the norm, we're looking at f and g being continuous, bounded, satisfying the boundary conditions, and defined between a and b. So we're looking at an eigenvalue problem. We want hy, where h is our self-adjoint operator, being equal to lambda times the weight times y. And because h is a self-adjoint operator, and h is a self-adjoint operator because we're looking at the Strum Liouville problem, we know that there are infinitely many distinct eigenvalues. Not only that, but we have something really strong about the eigenfunctions. The eigenfunctions, the different eigenfunctions are orthogonal to each other with respect to the inner product. That means that if you plug the two different eigenfunctions in the inner product, you'll retrieve something that is equal to 0.